And now we need to talk about continuous matter. So continuous matter could mean like a fluid or a stylus, pencil, or a gas, or an electromagnetic field. It doesn't have to be any particular version of continuous matter. I just mean something that's going to be described by densities as opposed to a finite amount of mass at a point or something like that. And at a classical level, continuous matter is really more fundamental. You run into problems trying to take point particles completely seriously at a classical level. You run into issues like, what is the force of a point particle on itself? Well, the point particle's field is infinite at its own position. How do you make sense of that? You can, but only by going back and appealing to continuous matter. So continuous matter is really more fundamental from the point of view of classical physics, which is all we're really going to do in this class. Now, to get into how we represent continuous matter and focusing on energy and momentum, I'm going to remind you of something you showed on the homework, which is that charge current conservation, del mu, J mu equals 0, follows from Maxwell's equations. Now, why did I call this charge current conservation? Well, if we write this out, recalling that the forecurrent vector is composed of the charge density rho and the current density J, then what is this? Well, this equation is del 0 J0 plus del I Ji equals 0, otherwise known as d rho dt plus the divergence of J equals 0. Okay, so this bottom equation you would have seen in electromagnetism class in this notation. This is the continuity equation. But this is the equation that expresses the fact that charge current is conserved. And you really do need this equation because conservation of charge current is a local statement, right? It's not that I can conjure up a positive charge right here as long as someone else conjures up a negative charge in the Andromeda galaxy. It's not how it works. That would violate charge conservation. Right? Charge conservation is local. It says that if suddenly there's net positive charge in my hands, it must have come in through my hands, right? Or negative charge must have flowed out, something like that, which is a much stronger statement than merely global charge conservation. Global, again, would be as if I got a charge in my hands and way off on the moon, a negative charge appeared out of nowhere. Okay? So this is the equation that expresses local charge conservation. And let's review why that is. I think the simplest way to think about it is to actually think about drawing a surface like, my hands. So let's do that. So we imagine some volume V bounded by some surface S. So V is the interior. And we take our equation and we integrate it over the volume, d rho dt d3x plus integral divergence of J d3x. And for simplicity, we'll keep the volume stationary, so we can pull the time derivative out. And now we've integrated over the 3 spatial coordinates, so I can write that as an ordinary time derivative of integral rho d3x. And what can I do with this one? This was all equal to 0. Well, I can use the divergence theorem. J dot dA. Okay. And so this says then, if you like, that the charge enclosed, Q enclosed, is equal to the, charge leaving the boundary. Whoops. The charge, I don't know, minus the charge flowing out.
The rate of change
Charge flowing out per unit time. Right. Okay, so that's the strong statement, that if charge ever changes inside my hands, I have to be able to account for it as charge moving through the surface of my hands per unit time. Okay? And that's really the interpretation of the current density J, right? What the current density J tells you is how much current, namely charge per unit time, would be flowing. So for example, Jx, the x component, is as if you drew a surface like this, where this is x hat, and you ask how much charge is flowing through this surface per unit time. So if you like, Jx times the area equals the current through this surface. Okay, so that's what we mean by charge density. So we're going to take this framework and we're going to try to apply it to energy and momentum. Those are also conserved quantities. Energy has the same property. It's not like I can magically, heat up the area in between my hands as long as something gets colder on Andromeda. Like, that's not the way it works, right? If energy inside here is going to change, it has to flow in. And so how would we represent that? Well, we would sort of want to consider some 4-vector. In the same way, that would give us a theorem that would say the change in energy is in some region is equal to the flux through the boundary. So you could imagine sort of trying to invent something like that, where it would be del mu E mu equals 0, where E0 would be the energy density, analogously to J0 being the charge density, and the spatial components would be some energy current. And you can sort of do this, but it's missing something, which is the frame dependence of energy, right? So one person's energy is someone else's mix of energy and momentum. That's a major lesson of relativity. And so this is kind of almost what we need, but we need a law that's going to encode all of the energy and momentum conservation together in one tensorial equation. And the claim, which none of the GR books derive, and with good reason, because it's quite tricky, and fundamentally, eventually we're going to go in the reverse order and use gravity to define this thing. But the claim is that in pretty much every circumstance anyone has ever come up with, energy and momentum conservation are encoded in an equation like this: del mu T mu nu equals 0. And this T is called the stress energy momentum tensor, because it's going to have all those things in it. Now, usually we shorten it and we just say stress energy tensor or stress tensor, and I'll probably say all of those things. I'll probably never say stress energy momentum tensor after today. But the claim is this encodes all of the conservation laws. And so in particular, del mu T mu 0 equals 0 is going to be conservation of energy. So the zero component in some Lorentz frame, and then we regard the other 4 as a 4 vector, and you can get the same sort of equation, right, that we had for conservation of charge, for conservation of energy. And then the way all this ends up playing nicely with Lorentz transformations is that the spatial components, T mu I equals 0, are conservation of the ith spatial, or just momentum. Okay? And that's really the way this thing is defined at the level of special relativity. It's consistent with treatments you'll find, for example, in fluid mechanics and so on, and we'll make connections shortly to try to see how this fits in. But fundamentally, we're just looking for a way to express conservation of energy and momentum for continuous matter. Now, there's another property which is even less obvious, but the stress energy tensor can always be taken to be symmetric in the 2 indices. Now, in quantum field theory, you sometimes define energy and momentum with Noether's theorem, and you find it's not symmetric, and then you improve it by making it symmetric, by adding total derivatives such that you still have these interpretations. In fluid mechanics, it just is symmetric. When we include gravity, we're going to find, in fact, that Einstein's equation requires it to be symmetric. And so if you argue with me about whether it's symmetric or not, ultimately I'm going to say, well, just wait. We're going to use this to motivate Einstein's equation. But Einstein's equation is correct. It's a correct theory of nature at the scales we can measure. And so fundamentally, it's gravity that tells you what stress energy is. That's how you fundamentally measure what energy, momentum, stress, and all those things are of an object. It's how it couples to the gravitational field. So that's what I'll fall back to if you have objections to these claims. Now, let me make some of this a little more plausible. So first of all, let's think about T0I equals Ti0. So what is the way we've defined it? Ti0 is the spatial part of the energy density 4-vector thingy, the analogous thing to the charge current 4-vector. So this thing is flux of energy in the ith direction. Okay? But what is this thing by our definition down here? Well, now we've got an I in the second index, and so we're talking about the ith momentum, but we have a 0 in the first index, so that's referring to just the density of momentum, just like the J0 referred to the density of current. So this is just the momentum density. Ith momentum density. Okay, just by the definitions I've written down. And so this is very natural. This is how we think about momentum in elementary physics, right? If there's some energy moving in some direction, some flux in the x direction, we'd say there is momentum in the x direction. And so this symmetry is very natural. Now the ij components, it's a little harder to think about the symmetry, and you can really go down a rabbit hole. asking continuum mechanics books or fluid mechanics books why the stress tensor is symmetric. There are various answers to that. And ultimately, I think the relevant statement here is you can make it symmetric, and that's extremely natural, and it's going to motivate general relativity. And then we're going to turn around and say, okay, general relativity proves that the right thing to talk about is a symmetric stress energy momentum tensor. Yes?
I'm just curious, would you say that Noether's theorem is incorrect?
Well, a theorem can't be incorrect, but is it the incorrect way to define energy and momentum? Yes. I think fundamentally, the answers you get for energy and momentum will depend on your special choices of total derivatives that you included. Right? The action is invariant up to a total derivative, but depending on how you write the Lagrangian, you'll get different answers for the other currents associated with time translations and space translations. Whereas if you just define it by coupling to gravity, you get a unique answer. Anything else?
I feel like you're not giving a complete argument.
That's absolutely right. And now I'm going to do exactly what I said and say the complete argument is the correct equation of nature, which we'll get to in a couple weeks, is Einstein's equation. And as a consequence of Einstein's equation, that stress energy is symmetric and, in fact, conserved. You get that out of gravity as well.
So we just have to trust you?
You have to trust me about a lot, yeah. I mean, physics is ultimately an experimental science, and you do want to derive laws from as few axioms as possible, but gravity is so fundamental. Einstein's equations is really going to be one of those axioms. I'm just thinking in a way some people are familiar with to motivate that, but ultimately the logic goes the other way. Yeah?
Is there anything in Wald that might help?
Nope. Wald says, in special relativity for continuous matter, energy and momentum are described by a symmetric conserved tensor.
There is some part in the Lagrangian to say about the difference between canonical.
Sure. But that's not going to help you derive that the symmetric conserved tensor is the right thing. It's just part of the theory. And if Wald doesn't explain it, you know there's no explanation. Except for gravity itself. I mean, this seems unsatisfying, but it shouldn't be, right? You want to explain the less fundamental things in terms of the more fundamental things, not the other way around. Often it's discovered in reverse. You first play around with the less fundamental because that's experimentally accessible, and then someone like Einstein grabs at the more fundamental, makes a guess, and then it's experimentally confirmed. And now you say, okay, we start with that more fundamental result about gravity and derive the rest from it. It's like this with quantum mechanics, too. This is a bit of a tangent, but if you've struggled with, quote unquote, understanding quantum mechanics and you find that very hard, it's usually because you're trying to explain quantum mechanics in terms of classical mechanics, which is impossible and backwards. Like, quantum mechanics is the fundamental theory. The confusing and hard thing is explaining classical mechanics in terms of quantum mechanics. So that's a sort of analogous statement. In gravity, everything is crystal clear. I promise when we get to Einstein's equation, you'll see instantly, and we'll emphasize how it gives you the symmetric conserved stress energy of everything in the universe. Yes?
Is there physical meaning to the indices being up and up, and then up and down and down and down for the stress energy?
Well, I've introduced it in terms of upstairs indices. Is there physical meaning? There's certainly mathematical meaning in the sense that I want to regard the components of, so for example, if I set this one to 0, I want to have upstairs indices remaining so that I can regard it as a 4 vector, not a 1 form, analogously to the charge current 4 vector. So yeah, there's physical meaning, but ultimately it will freely raise and lower the indices as we like. Okay. So now let's think about how this relates to some things we know. So first of all, the traditional way of thinking about naming these terms is, let's think about it as a big matrix. So up here in the 0, 0 component, that's just energy density in some frame. So these are all frame-dependent notions, but the claim is this thing transforms like a good tensor. So we put energy density up here in the 0, 0 component. And we can think of these terms here and these terms here. Since it's symmetric, we might as well just think about it as momentum density. So the three terms here are momentum density. And similarly here, this is also momentum density. And then what goes here? Well, this is the stress tensor. So that's maybe not so helpful if you haven't studied this object in continuum mechanics or something. And so let's think about the stress tensor like this. So now let's think about what this term is, txx. So the second component is x, so it has something to do with x momentum. And the first component is x, so it's like the x current of x momentum. So txx is the x current of x momentum. So I can draw the same picture I drew for the x current of charge a little earlier. I took a little patch of area. I said it's normal to the x hat direction. And I thought about how much charge was going through this surface. Well, txx is telling us how much x momentum is going through this surface, which is a little different because of this x momentum. So one difference is if you the charge current, if you had, 100 plus charges moving to the right at some speed and 100 minus charges moving to the left at some speed, that would be 0 charge current, because those plus charges carry charge to the right, those other plus charges carry charge to the left, and there's no net flux. But if we're asking about the momentum, well, the ones moving, I'm doing my own right. Well, the ones moving that way are carrying x momentum that way, positive x momentum that way. But the ones moving this way are now carrying negative x momentum this way, which is the same as positive x momentum that way. So it's actually counting both. That's a sort of difference. Okay? So it's really counting the total amount of momentum that's kind of moving around in this patch of area. And if you think about the units, well, it's supposed to be, we had an equation up here where we did this thing for J. We said Jx times the area was the current through the surface, the amount of charge through the surface. So here, it should be Txx times the area is the amount of momentum per unit time. Momentum per unit time through the surface. So x momentum. But what is this? When you talk about the change in the x momentum per unit time, per unit area, that's just the pressure. So Txx is pressure. Yeah, question?
Is this defined as an infinitesimal point?
Yeah. Yeah, so this should be an arbitrarily small little surface, just like current density refers to an infinitesimal point. Mm-hmm.
So pressure is force per unit area, right?
Force per unit area. So this is dp dt. So if you think of force as dp dt, change in momentum, this is like dp dt. But we want to think of force as more of an emergent thing. We want to just talk about energy and momentum. Okay, so that's why that's pressure, and Tyy would also be pressure, and Tzz would also be pressure. And these are the traditional names for it, but a civil engineer making a bridge would not call these pressure. Does anyone know what a civil engineer, someone working with bars and so forth, would call TXX, TYY, TZZ?
Shear stress.
It's not shear yet. Those will be off diagonal.
Strange.
Strain has to do with the response, I think.
Stress.
It's part of the stress tensor.
TXX.
We could think about it as force per unit area. Suppose I took this object, stylus, and I pressed really hard and I compressed it. Yeah. So, that would mean that if you stuck something in there, it would feel squeezed on. There would be force per unit area. So that would be compression, or if you pulled on it, it would be tension. So tension is like one of the first forces you learn about when you do freshman physics, right? There's always these wires that carry tension and so forth. So that's described by a diagonal component of the stress tensor. Now, the other thing that can happen, in a fluid, you could have viscosity. So in a fluid, it could be that when, this part of the fluid wants to flow up, it drags some other fluid with it. So that's now a force per unit area in the up direction, but between neighboring fluid elements in the side direction. So that's an off diagonal element of the stress energy tensor. And so you might call that the effects of viscosity, but the traditional name for the off diagonal elements are shear. So it's interesting that we've adopted the fluid mechanics names for the diagonal elements, namely pressure, but the mechanical engineer's name for the off diagonal elements, namely shear. And shear is also important, look, I'm holding up a bar. Well, why isn't it falling? Why isn't this side falling to the ground? Right? Gravity's pulling it down. Well, there's a shear force from a neighboring element holding it up. Right? It's the only reason this pen doesn't fall. So that's an off-diagonal force, off-diagonal element, rather, of the stress tensor. Okay. Maybe I should draw a picture for shear. EXY, shear, or, X current of Y momentum, if you like. So there the picture is. We're interested in the current in the X direction, but now there's a kind of, I don't know, I'll just sort of write it as PY with an up or something. Interested in how much Y momentum would cross that surface per unit time. Okay? And for completeness, let me just write out T00. We already said that. That's energy density. And T0I, which is the same as Ti0, is momentum density. Now I realize I forgot to give myself a reminder not to use the bottom right of the screen, since it'll be covered up by my picture. So probably the online video will have some covered up stuff. Okay. So that's the best I can do with the stress energy tensor. And I'm not going to claim it's the best anyone can do with the stress energy tensor, but I honestly think it's pretty close. There's just not that much more to say. Ultimately, its importance comes from the fact that it appears in Einstein's equation, which we are now just motivating. Now, I should say that fluids and bars are not the only kind of matter. And you definitely shouldn't think of all energy and momentum in the universe as being associated with fluids and bars. So just as another example, you know, E and M, electricity and magnetism, has a stress energy tensor. I'm not going to write it down. You're going to do a homework problem this week. But for example, you know, T00, the energy density is, there's some unit dependent factor. I'm just going to take it to be 1. I don't have this in my notes. E squared plus B squared, right? Remember this? Energy density in an electromagnetic field. That's a real energy density that will gravitate just like any other energy density, and it's not somehow associated with matter, right? It's electric fields. And similarly, Ti0, now I don't know the normalization though. I might have to write proportional to. Let's do proportional to for both of them. That'll keep me safe. Okay. Proportional to. Okay, and there's also Tij, and depending on who taught you electromagnetism, they may or may not have included this, but it's part of the theory that electromagnetic field carries stress. Yes?
This might be another, we get to this later kind of thing, but the stress energy tensor does, if E and M has a different one than, say, like what we were talking about above, then how does it all like come together into one thing?
Oh, you add them together. Yeah, you just count up all the energy and momentum. So that's a nice thing about conserved quantities. They're additive. Okay, and the momentum density, I think, is particularly interesting to think about, to divorce yourself of the idea that momentum is somehow masses moving around. It's really not. Right? You could have static electric and magnetic fields, and you'll have momentum density. You just will. This is the momentum density of the electromagnetic field. So you should think of momentum as just another conserved quantity, which is in fact intimately related to energy, because energy and momentum mix under Lorentz transformation. Now let's do another example. So I guess E and M was an example, but I didn't do it in much detail. Let's do one that's much simpler that we can write out explicitly. So let's just consider a bunch of particles at rest in some frame. There's a funny name for this, which is actually quite standard. It's dust. I think you're supposed to imagine like dust grains on the windowsill or something just sitting there. But this is three-dimensional space. The particles are filling space.
Well, dust can't move, so it can fit in here.
Well, it'll be moving in some frame. So, in this frame, in the rest frame, so now that we have this situation where there's a bunch of particles static in some frame, well, we have a preferred frame. We call that the rest frame. So what is the stress energy tensor going to be? Well, we just look up what its components are interpreted as. T00 was energy density. So that's just, we're going to call that rho. That's the mass density because everything's at rest. So energy and mass are equal. So rho is the mass density. And in this frame, none of this matter is moving, so there's no momentum. And then there's also no fluxes of momentum, no stress, if you like, or no pressure. And so we have that. And now what we're going to do is play a game that we're going to play a lot in this class, which is we're going to take an equation that really only... Why it does that? That really only held in one frame. And we're going to find a covariant notation, meaning one that will hold in any Lorentz frame. So let's introduce the 4 velocity, u mu, the 4 velocity of any of these particles. You can think of it as a fluid 4 velocity if you want, but they're all just sitting there. So in this frame, it has components 1, 0, 0, 0. We worked that out maybe too laboriously for such a simple thing last time. And if in a frame where a particle is just sitting there, it's only moving through time, its forward velocity is u mu. So these equations hold only in one frame. These are not going to be the equations we want. But notice we could instead write T mu nu equals rho u mu u nu. So let's check that. So T0, 0 is rho times U0 times U0. Let's check that. T0, 0 is rho U0, U0, but U0 is 1. Okay? So that works, because that agrees with up there, right? And similarly, T0i is rho U0, Ui, but that's going to be 0 because Ui equals 0. And so that also agrees, and similarly, Tij is going to be 0 because Ui is 0. So this equation here in black is literally the same equation as the one in the matrix, but this equation is tensorial. This equation follows the rules of tensor notation. It's got one upstairs index mu on the left and one upstairs index mu on the right. One upstairs index nu on the left, one upstairs index nu on the right. Okay? So this is valid in any Lorentz frame. Okay? So it's a very simple trick, but we want to think of what we mean by dust as the equation valid in any frame. And we would then promote this, the forward velocity. It doesn't have to be every particle has the same forward velocity. We could just have a different forward velocity at each point in space in our dust fluid. And then the stress energy tensor would still take this form, and rho would be the space-dependent energy density, rest frame energy density, and then u mu would be the fluid forward velocity. Okay? So it's a super trivial example, but in fact, you can basically derive the fact that the universe must be expanding by plugging this into Einstein's equation. In fact, Einstein did that, but he was unhappy with it because he didn't want the universe to be expanding. So he added a cosmological constant to kill it off. And he later called that his biggest blunder because he missed the opportunity to actually predict that the universe was expanding. So there's actually a lot of power in this very simple expression. And this is a good approximation. Well, no, you need dark energy as well. But if you didn't know about dark energy, this would be a good approximation for the dynamics of our universe today. It's mostly in separated point particles, namely galaxy clusters, that don't have very much peculiar velocity, that are mostly sort of just sitting there. Okay, any questions?
Do we have a way to express the EM stress energy?
It's on the homework, yeah.
Oh, okay.
Okay, so that's our dust. Let's do one more example. We're going to call it a perfect fluid. It's funny how these historical names have value judgments in them. I don't know why these fluids are perfect. But a perfect fluid is one described by not just the rest energy density rho, but also some isotropic pressure. So many things behave as perfect fluids, including ideal gases. So isotropic pressure, again, in fluid frame. So that's how we avoid the fact that pressures are frame dependent. What we mean here is the pressure in the frame of the fluid. Yeah? Oh. Which is itself a kind of subtle thing to make sense of. You have to define some averaging procedure. And in fact, even deriving the equations of fluid mechanics from more fundamental descriptions is quite challenging, especially in special relativity. We still put rho in the spot where the energy density goes, but then we put P in the XX, YY, and ZZ components. And we put zeros. Wow, those P's are very hard to distinguish from the rows. Let me try that again. So let's delete them all. We'll have very exaggerated row here, very curly and slanted, and very upright P's. Okay. So this again holds in the fluid frame. One special frame that we single out because we think a fluid has such a frame where like the mean velocity is 0, for example. And then we try to do the same game of finding a tensorial expression. And this one is actually a little trickier to find. I'm going to tell it to you and then we'll check it. So if we want to build a good tensor equation out of the ingredients. Oh, I also need the, let me write the fluid 4 velocity again, just so we have it on the screen. So it's the same thing. The special frame is the one where the fluid 4 velocity is just 1, 0, 0, 0. So these two equations hold in the frame. So now the task is, how can we write this top equation for the stress energy tensor using just the ingredients u mu equals 1, 0, 0, 0, rho, and p? And in fact, you'll find it's impossible unless you bring in one other ingredient, which is the metric. So we're really going to have to use the space-time metric now, which is fine. That's a good tensor. We have that around. And the answer is going to be that T mu nu can be written as rho plus P u mu u nu plus P eta mu nu, the space-time metric, or inverse metric in this case. So this, when I first saw this, I thought it looked crazy and weird and didn't understand it all. And I still don't really know like any comforting words for why it looks so different, but we just check it. So let's do the same thing we did above. Let's see if it works. So let's try T 0, 0. So T 0, 0 would be rho plus P u 0, u 0. This is just 1. They're each 1. And P eta 0, 0. But remember that eta is the diagonal matrix that's got minus 1, 1, 1, 1 on the diagonals and zeros elsewhere. So eta 0, 0 is minus 1. So you can see the P cancels the P, and indeed we just get back rho. That one works. And let's keep going. T 0I, that's going to be rho plus P u 0 ui, but ui is 0. So this whole thing is gone, plus P eta upper 0, I, this thing is also 0. There's no off-diagonal elements in eta. So T0I is 0, which is what we wanted. We wanted all the off-diagonal elements to be 0. And it's manifestly symmetric just from the way we constructed it, so we don't have to check I0 separately. And finally, let's do Ij. So Ij is rho plus P Ui Uj. These are both 0 plus P eta Ij. Eta Ij is just the Kronecker delta, right? Or the unit, the identity matrix in 3D, if you like. So that's P delta Ij, which is also what we wanted, right? Because if I is not equal to j, it's 0, so those are our off-diagonal elements. And if I is equal to j, it's 1, and we get the same pressure P on the diagonal. Okay, so this is the kind of game we're going to play over and over and over in the course. We won't do it this thoroughly and slowly every time, and there'll be homework problems. But the name of the game is you take some set of equations that hold just in a special frame where you already have some pre-existing notion of the theory you're considering, like in this case, a perfect fluid, and then you rewrite those in a tensorial way, where you only use good tensors like the 4 velocity and the metric, and you put them together to make a symmetric conserved stress energy tensor. And this holds in any Lorentz frame simply by the tensor notation. And that's partly why we work so hard to establish this tensor notation. And this tensor notation is going to survive in general relativity, and the way we're going to treat perfect fluids in general relativity is just by plugging this form into Einstein's equation. Yes, and tell me your name?
Carl.
Carl, okay.
You say this holds in any frame, but the previous equation you wrote a while ago is different and also holds in any frame? I'm confused.
Oh, this is for a perfect fluid. And so the previous equation was for a pressureless fluid. Yeah, exactly. So this is, we've done 3 examples. I didn't really do electromagnetism, I just mentioned it. But the idea is with each example, you take your theory that you already believe in, you write it out in some frame. You already believe it, right? We know that this is the stress energy tensor for a perfect fluid because that's the point. It has isotropic pressure and so forth. And we say, well, how am I going to write that in a frame invariant way so I can use it in special relativity and ultimately in general relativity? And so you just translate this simple looking equation into this more complicated looking equation, but the more complicated looking equation is ready to use. Yes?
Is this kind of equation works for this frame and also works for every frame unique?
In this case, it's clear that it is.
In any context, how can we be sure that this is a frame unique?
Sometimes you can't. I think in special relativity, you're always okay. In this case, you could go through and just write out the general. I'm sure you could prove this is unique in special relativity. The issue when you promote to general relativity is you can just randomly add terms that are proportional to the space-time curvature, and those will go to 0 automatically in the flat space-time limit. And so there is some non-uniqueness in saying what you mean in general relativity. There's a notion of minimal substitution, which is usually obvious. You sort of don't add any of those terms proportional to curvature, and every theory we'll consider has a natural generalization, and those are the ones that are assumed to hold as the statement of how fluids or electromagnetism or whatever behaves in general relativity. But in general, that's not a fully valid prescription. Usually you go after the idea that it would come from a Lagrangian, and then you really do get a unique curved space-time version.
So in general, we work in this frame, try to come up with a general tensorial expression that
Yes.
should work for every frame.
That's right.
But that might or might not be unique depending on
In curved space-time, yes. Yeah. It would be nice to directly test, for example, the way Maxwell's equations are promoted to general relativity is used all the time because how could it not be? There's so many reasons. The Lagrangian framework, the minimal substitution idea, but it's never been directly tested. Okay. Now, these perfect fluids actually represent a lot more than you might think about as fluids. So, for example, when we get to cosmology, way at the end of the course, we'll talk about a fluid with negative pressure equal exactly to the minus of the energy density, and that's the dark energy. So it's a fairly flexible framework for discussing for discussing things you can plug into Einstein's equation. There's one more thing I should say on the fluids. Let's think about energy conservation. Remember that we asserted that part of the framework is that it must be true that del mu T mu nu equals 0. This is conservation of energy and momentum. So let's think about what this implies. We can do a little calculation. So let's do it in the example of our perfect fluid up here. I have to get it out from under there we go. So let's just start computing. Let's see what we've got here. So del mu, I'm going to plug into T mu nu, so I'm going to have some terms. I'm going to have del mu acting on rho plus P times u mu u nu. So the convention is that the derivative acts on just the thing to the right of it. So here the derivative is not acting on u mu u nu. If I wanted that, I would use parentheses. So I need to use the Leibniz rule here and add a term rho plus P del mu acting on, let's just do them all out. So I need a term where it's acting on u mu, the first one, but not acting on u nu. And I need a term rho plus P where it's acting on the second one.
I'm guessing from both intuition and your attitude about this, the last one's going to go to 0.
The last one?
Like the last term, the du.
The pressure one? So that's this one, which now I've covered up under this.
The d mu u nu. Yes, that one right there. Like
I don't think so, not in general.
there's terms where p equals 1.
So, and then this term here, del mu, let's just be very explicit. So then let's write, there's one last term, P. Now, eta mu nu is constant, so it doesn't have any derivatives. So we'll bring that out, eta mu nu del nu. Oh, what am I doing? P is not constant, that's the whole point. Okay. All right, so this is just, I've now written out stress energy conservation for our...
Won't it be del mu p?
What's the free? Yeah, nu is the free index. Thank you. Really botched that term. Okay. So I'm doing del mu, eta mu nu p, but I can bring out eta mu nu, del mu p. Okay, thank you. Hopefully we're back on track now. Okay, now we want to make some sense of this. And the thing to do is basically, quote unquote, take the time and space components. But we don't want to do it in some specific frame. Now we want to do it in the rest frame of the fluid to interpret this in the way you're used to thinking about it. And so to do that in a tensorial way, what we really mean is we need to consider the part of this equation proportional to u mu and perpendicular to u mu. So the part proportional to u mu is like the time component in the rest frame, and the part perpendicular is like the space component in the rest frame. I think I'll have time to show you at least the time component. I might put the space component on a later homework. There's enough already for this week. But let's do the time component. So the part proportional to u mu, well, that just means we dot with u mu, right? Anything that was perpendicular to u mu, well, that by definition goes away when we dot with u mu. Okay? So the part proportional to u mu means contract this equation with u mu. It's going to be u nu because that's our free index, as you've already pointed out to me. So let's do that. So let's take this equation and contract it. Let's just be very explicit. So u nu del mu rho plus p u mu u nu, that's the first term, plus u nu rho plus p del mu u mu u nu plus.
You mean contracted with u lower nu?
Yeah, I sure do. Can't do that because we had nu up. So dot with u upper nu if you like, contract with u lower nu. Very good. So let's just work on the, let's just work on the first term here. So this term. So what do we see here? Well, all this stuff in the middle is kind of a distraction right now. The thing to notice is we have u contracted with itself. And you may recall from the definition of the 4 velocity, u mu u nu. It's always minus 1. That's the definition. Or one definition. And so this term, the u nu and the u nu go away. This just becomes del mu rho plus p u mu. And actually the same thing happens to this term.
Why is there not a negative sign?
Because I'm just falling apart. There should absolutely be a negative sign. So we have u nu, which is minus 1, pulling down a minus sign. The same thing happens here, minus rho plus p del mu u mu. And we had these other terms. So this one is going to be a little more interesting here. So we have rho plus p. I'm going to put the u nu in front of the derivative. So u mu u nu, put it up again, u lower nu u upper mu. Still haven't figured out why it does that. Lower nu, u upper mu, partial lower mu, u upper nu. Okay, so that's this term. And this one is interesting. This is going to turn out to be 0 now that we've contracted with u. And let me show you why. So it also comes from the normalization condition. So the normalization condition, we have u, let's make it nu. U nu equals minus 1. That's true. So if we take a derivative of both sides, then what happens? Well, the derivative of a constant is 0. Del mu minus 1 is 0. But we can expand this one out with the chain rule. There's Leibniz rule. There's two terms. Del mu u nu, u lower nu, plus u upper nu, del mu u lower nu. But these are really the same term, because we could just, as you showed on the homework, we could just lower this nu and raise this nu. And you can always do that. There's a derivative here, but the metric you bring in will commute through the derivative. So these are really the same thing. So this is really just twice u nu del mu u nu. And so that proves that this thing, u del u, is actually 0. So this implies that this is equal to 0. So that's a funny little index argument. And the more problems you do like this, the more this will seem natural, but tricks like this are important for doing these kinds of calculations, and you'll see some this week. So what that tells us is we have u nu del mu u nu here. So this thing is in fact 0. And then there was one last term that I left out, this one. So we can write that as, let's try to keep things. We can write that as plus u lower nu eta mu nu del mu p. We'll just leave it like that for now. We're getting there.
I see where that's going.
You see where it's going?
Well, that one specific term, yes.
Okay. Where's it going?
It's going to become u super mu del mu p, which will cancel out with the first term.
Right. So we look at this and we see that that just raised the index on mu, u mu del mu p, and minus u mu del mu p. So we can, this was the green term here. So we see there's a cancellation of this term and this term. Now what do we have left? So we have minus del mu rho times u mu. We have minus rho del mu u mu. And we have minus p del mu u mu. Okay, and this was all equal to 0. And so what do we have here? Well, usually this would be written del mu. Guess we can, no, let's keep them as minus. Del mu rho u mu, because the first two terms can be combined together by the Leibniz rule. And maybe we'll move this one to the other side. P del mu u mu. And we're almost to a punchline. So remember, this was stress energy conservation, dotted in finding the component parallel to the 4 velocity mu, like the components that you would call energy in the fluid frame. So to interpret this, we can do a non-relativistic limit. Non-relativistic limit. This will go a little fast because we only have a few minutes. Remember that in general, we wrote u mu as gamma 1v. But that'll just be approximately 1v in the non-relativistic limit, because gamma will be approximately 1 when v is very small. We'll also have norm of v is much, much less than 1. That's just, well, I already used that in deriving this. And then the other thing in the non-relativistic limit is pressures will be small compared to energy densities. This is basically saying that, kinetic energies are small compared to rest mass energies. There's a lot more energy in a mass than how fast it would be moving in the non-relativistic limit. And so in the non-relativistic limit, we get to drop the pressure entirely. So in the non-relativistic limit, we just have the equation del mu rho u mu equals 0, or using that u mu is just 1 comma v, we have del 0 of rho times 1 plus del I of rho times vi. That's from this approximation. And if you've done any fluid mechanics, you've seen this. This is the statement that d rho dt plus divergence of rho v equals 0. This is sometimes called the continuity equation. And your fluid books will tell you this is conservation of energy, and indeed that's what we got it from. Okay, that's it for special relativity. Next time we will start talking about gravity.